Thank you very much. We're really proud to be here today. We know this is the first running of this conference, and it's something that we're really excited about to see more offensive security conferences coming out, especially in Europe. We want to thank Blue Frost for having us here and allowing us to share this information with you. So this is the art of evasion, modern VMware exploitation techniques. Today we're going to be going over lots of different areas. The first thing we'll do is kind of describe the attack surface that exists in VMware, both in VMware Workstation and Fusion. We're going to cover a little bit of the attack surface that we have known to have bugs in. We purchase vulnerabilities, and so we purchase vulnerabilities in several of these components. We'll kind of talk about what people are finding in these areas. And then we're going to go over a set of exploitation case studies, starting off with kind of an easier to exploit bug, and then moving on to really, really complicated exploits with a lot of steps where you're really going to need to be caffeinated. So definitely drink. Maybe beer like this guy would be good. So, first, quick introductions for those of you who don't know who we are. My name is Brian Gorenc. I'm the Director of Vulnerability Research inside of Trend Micro. My primary responsibility is running a program called the Zero Day Initiative, which represents the world's largest vendor-agnostic bug bounty program. So what does that mean? That means we work with researchers around the world, and as they find zero-day vulnerabilities and write zero-day exploits against those vulnerabilities, we purchase them for money. And then we work with the affected vendor to get them fixed, at the same time providing intelligence to the Trend Micro product lines so that they can detect zero-day attacks in the wild. I'm also responsible for organizing and adjudicating the ever-popular Pondo and hacking competition, which is actually happening in March. So if you do have exploits against some of the targets that we are putting big money against, you can come out and win up to $2 million at this contest. So I've done a lot of work in the past developing code in C and C++. I've done Microsoft bounty submissions with Abdul here, worked on several patents for exploit mitigations, and done a lot of bug hunting myself. Malicious input on Twitter if you want to follow me, though I'm not very noisy on Twitter, so probably not the best follow.
All right, so my name is Abdul. I'm a researcher working at the ZDI. I've been working at the ZDI for the past 5 years. So I mainly do root cause analysis, bug hunting, and exploit development. I'm also the ZDI case lead, which basically means that I'm the guy who dispatches all the cases that we get through the program to analysts, make sure they actually flow and price these cases. So if you guys have any questions for me or about like an offer that we sent you that you didn't like, you can always talk to me about it. You might actually find me after this presentation in the bar, teaching Moti there how to play FIFA later on Nintendo Switch. Yeah.
We got money on this.
So I did a lot of research in the ZDI. Basically, I was one of the guys who wrote the Pwn for Fun exploit back in 2014. I was responsible for the render exploit specifically. I've also was part of the team which was led by Brian for the exploit mitigation bypasses, which we won $125,000. So I was specifically tasked with isolated heap. I've done a lot of research on Adobe Reader, and you guys can find me on Twitter if you want to follow my work, or if you want to know the latest weather forecast in Montreal or something. So now Jasiel is going to introduce himself.
All right, I'm Jasiel Spelman. I usually go by Wandering Glitch or just Glitch. I'm the ZDI research lead. I've been with ZDI for about 6 years, or just shy of 6 years. Try and do a lot of static analysis, and also trying to augment my reverse engineering abilities by using automation. So I end up writing a lot of Python for, say, IDA or Binary Ninja to rename functions, identify structs, things of that nature, and we'll kind of go over that a little bit later on. And I'm Wandering Glitch on Twitter.
He also loves CTF challenges.
Oh yeah, I forgot. So at Blue Frost had a kind of CTF challenge, an exploitable for entry to Echo Party, and I think I was the 7th or so person to submit a working exploit. Didn't end up going to Echo Party because timing didn't work out, but it was kind of a fun challenge and nice way to meet Blue Frost. Actually, that was my first communication with Miguel, and it's nice to be able to meet in person.
All right. So let's get started. So let's start digging into VMware. The first thing we want to do is level set everybody so they kind of understand where we're going to go and where to look for bugs and how to exploit those bugs by looking at the architecture of VMware. Now, most of you in this room probably have either used VMware or used one of their competitors. They all kind of look the same. In this case, they have several guest operating systems sitting there on top of some sort of management layer, and these guest operating systems are communicating with this management layer through I/O over a virtual CPU. And you can interact with this CPU either directly or you can actually use some of the libraries that are provided by the vendor, in this case, VMware tool libs, to actually do some of the communication back and forth. But as a bug hunter and as an exploiter, we're kind of interested in what exactly is happening here. If we can find some vulnerabilities in the way that data is transferring over this trust boundary, we may be able to actually exploit those vulnerabilities and execute code on the host operating system, which is actually our goal. We don't want to stay in the guest operating system. We want to move down to the host operating system, and we're hopefully going to show you that today. But the first thing we want to do is take a look at the attack surface that is important to our discussion. And we're going to be covering 5 different parts of the attack surface exposed by VMware. First, we'll be looking at the backdoor channel. Then we'll be looking at guest RPC functionality, followed by SVGA 2D, 3D communication or graphics, XHCI, and virtual printing. Now, all of these are areas where there has been research either in the public space or being purchased through our program, and there has been bugs discovered here, so it's kind of important to the actual end discussion of exploiting all of these vulnerabilities. Now, the fact that there's a channel called backdoor in any piece of software is a terrible, terrible name. But that is what it's called, the backdoor channel. And they do this communication by hijacking the in and out instructions of the CPU. And then they're using that hijacking method, they're actually able to move a lot of commands back and forth. Multiple commands are supported, including extracting information from the host, using those commands to actually do guest to host RPC communication. And all of this is done over special I/O ports. And the interesting thing about the backdoor is that it's always open and always enabled. So it doesn't matter if you have the libraries installed, you can always reach the functionality in the underlying hypervisor through this backdoor channel. Now, if we're trying to visualize what that looks like, it looks like this on the screen. You can see that there is lots of different commands and functions that go over this channel, including RPC, which supports a high and low bandwidth mode. There's other functionality and other commands that are available. And then there's TCLO, which is actually used for host to guest communication. And it's not something we're really going to be talking about today because we actually want to go the other way, guest to host. So in the backdoor channel, you can actually learn about a lot of the commands and functions that it's provided by looking at some of the open source tooling that's available from VMware on their Open VMware Tools repository in GitHub. Specifically, you want to look at the header file backdoor_def.h, where it defines a lot of the commands that we're interested in here. And so you can see there's git, dist-geo, a bunch of different stuff that's going on in the backdoor. But in future, we're going to be talking about the RPC, which is one of these commands that's available. But there is quite a bit, and actually Abdul can talk to you about some of the work that we've done in hijacking clipboards using this channel.
So you want to put pressure on me on this now?
Yes.
Okay.
Yes. Pressure's on.
So basically, the backdoor channel supports multiple commands and functions. So we presented last year at DerbyCon ways that we can use certain backdoor functionality to hijack the host OS clipboard from the guest OS without actually having the VMware tools installed. So this is really interesting, and Joshua Colonel Smith wrote a Metasploit module for that. There are also some functions supported by the backdoor that would actually tell you if you're in a VM or not. So if you're doing any post-exploitation stuff, you can just call that backdoor function. It's going to tell you whether you are in a VM or not. So that's quite useful for post-exploitation.
And there's also been some leaks some memory leaks in the backdoor that have been leveraged by some pwn contestants that you'll actually see come along here when we talk about exploitation of the use after free vulnerability that we're going to talk about in a minute. So there is vulnerabilities that have been discovered just outside of guest RPC, which is one of the methods, but it's kind of interesting. So invoking the backdoor, it's relatively simple. All you have to do is put some magic values and some registers and call the in instruction, and then you'll execute some code inside of the VMware VMX process. The magic number you want to put in EAX is basically VMXH. Then you're going to put your command-specific parameters in EBX, or at least a pointer to them, and then you're going to put your command number in the, ECX, And you're going to use the 1E command specifically to reach RPC functionality, which is what we're going to be talking about next. Then you're going to put whether you're going to be using the high or low bandwidth modes in EDX, and then you're going to call the in instruction. And that's going to allow for that data to transfer over that trust boundary and allow you access into the VMware VMX.exe. Now you can actually execute commands over the backdoor channel, and specifically the 1E command guest RPC, by using a tool that's provided by VMware called RPC tool. And you can use it to query the different functionalities that is available over the RPC command. And it is available in Open VMware tool, so you can kind of understand what it's actually doing underneath the covers. It's really easy to use. It's exactly what you see on the screen here. RPC tool VMX.capabilities.tools is upgradable. We'll call that RPC function and return the value back to the guest host, or the guest operating system. But you can see all the different commands that are actually available by reverse engineering VMware VMX, and you can see all of the different guest RPC functionality that's available. And if you cross-reference some of those strings, you can actually find the function handlers that are going to handle that code and then start looking for bugs there. So kind of giving you an idea of where you can look based off of what's available in your specific installation. Now, it's important for us to also understand how this looks like as we're going across. Not only do we want to understand, what functionality is being called when you call a specific RPC, possibly when you're trying to do some interesting stuff related to exploitation. And we did this by using a little PyKD, and Abdul can explain exactly what we did there to visualize the RPC calls.
So part of our tooling efforts in VMware was specifically done because we were trying to write exploits, specifically use after free exploits and heap overflow exploits. And we were specifically targeting RPC, so we needed a method to see our requests going back and forth. So we did a little bit of reversing, and we found out that the RPC requests are being parsed in one function. So what I did is basically wrote a small PyKD script, just set a breakpoint on that function, dump the RPC request, and then continue execution. It's as simple as that. And this is how it actually looks like in action. Simple PyKD, breakpoint. So basically, it's just going to dump the RPC request. So there are a lot of RPC requests going back and forth, even if you don't do anything on the guest. There's like some information being set back and forth. So also as part of the tooling stuff, and since we're a Python shop, basically, we wanted some kind of toolkit or tool chain, basically, to query the backdoor interface and to send RPC requests through Python instead of just like writing the whole thing in C++. So we figured out a way to do it. Well, actually, we figured out 2 ways. Personally, I worked on the longer way or the harder way, which is basically writing a C Python module, compiling it, and then importing it in Python. Jasiel kind of was nice enough to tell me that I did it the wrong way, and basically he did it through C types. So if you want to explain that a little bit.
So it's mostly wrong for what I end up doing. We're definitely a Python shop, and there's a Python RPC module that I use called RPC, where you can kind of ship Python code off to your endpoints, which ends up being great if you just want to ship something to a VM and then run it, but from that VM all remotely. And it just works out great if you're trying to do it across a bunch of VMs all at the same time. So pure Python is definitely what I try and strive for in those cases, especially since performance isn't too much of an issue. So with C types, because in the C module or C++ module and the C Python module, all it was using was calling hard-coded assembly. We already know what those opcodes are going to be and what the byte equivalents are, and so I can just drop that into C types, allocate a buffer with it, copy it over, and then either call virtual protect or mprotect to mark it as executable and define a function there with C types. And it'll just automatically box and unbox all the Python objects so that everything will get sent properly, and we can just call things with a very simple call. Ends up being very easy to ship to the endpoints.
So just to recap this video real quick, basically I was just showing my C types module being compiled, and then I imported it from Python and executed disk.shrink, which is basically an RPC function that we can execute from a non-privileged context. So it works well.
All right, so what's interesting about this is there have been several bugs in guest RPC, and we're actually going to talk about 2 of those in the exploitation section, give you an idea of what's possible using some of these toolings that we've developed and blogged about on our platform. The next, we're going to be talking about SVGA, 2D and 3D graphics. There's been a lot of research here done by probably many in the room, but it's not this section of the code is not very well documented, and there have been several interesting SVGA bugs that have come out over time. One that we'll be talking about at the end of the presentation was actually an uninitialized stack variable that led to an arbitrary free that was used by Chihu360 at the Pwn2Own contest. The bug itself was interesting, but the exploitation of the bug is very, very complicated, and it does require actually a decent amount of reversing to understand what's going on. And fuzzing this area is not that easy. There's been some research done by Keen about fuzzing this using bare metal, which Abdul's done a little bit of this, so he can give you some guidance there.
I remember Keen, they discussed something about fuzzing shaders, and they briefly mentioned that they fuzzed the shaders in VMware through bare metal, specifically through MetalKit, which is something that VMware released and open sourced years back, and it allows us to assemble small programs and just run them in bare metal. I've personally tested this, and I fuzzed the backdoor interface using that. It was pretty fast, and I was able to trigger like previous bugs, so it works well. And I think they actually found bugs through that as well.
Yeah, so because it's not well documented, you can actually use some of the open source available code and information from the guest drivers to actually help you out in your reversing effort. And because Jasiel loves to write code that helps his reversing efforts, he's going to be talking a little bit about what he did here to actually help rename some of the functionality that he gets out of IDA-Pro.
So one of the things that VMware released ages ago is VMware-SVGA, which is just a repo that has effectively a reference driver for the guest to use to interact with the SVGA device. And as part of that, they release a lot of types. Now, the types on their own are pretty worthless, but all the SVGA 3D commands start at decimal 1040, and I was able to find a function that was adding 1040 to a register, and it ended up being that it was iterating through a loop and adding that to the index. That function was also referencing a structure in memory, and I was able to look at that and then compare it to all the types. And so here we have these structs that I'm creating in IDA, and it's just a pointer to the function, to the handler for a specific 3D command handler or function or ID, sorry, followed by a function type, and then 3 D words that just seem to be unused, I'm assuming for either padding or just for reserved in case they ever need it in the future. It ends up working out pretty well, and it at least gives you some insight into how the SVGA code works within VMware VMX. There's also a lot of strings that you can use to get more information about where code is common. Like for example, you'll see a lot of .c files that are referenced all over the place and kind of gives you a better inside picture as to how they've structured things.
Kind of one of the newer attack surfaces that's available is XHCI, or Extensible Host Controller Interface, really used to define the description of the host controller for the USBs. It supports USB 1, 2, and 3, and actually wasn't really fully supported until version 9 of Workstation. So it's relatively new from an attack surface perspective, and so there hasn't been a lot of research there about this one. So like we said, it's from a vulnerability development perspective. This is one place where you can look because, again, there hasn't been much. And I think one of the only publicly known vulnerabilities in this attack surface was actually leveraged by Tencent Team Sniper at Pwn2Own 2017. And this vulnerability dealt with the way that VMware Workstation maps guest physical memory. And if it fails to map correctly, it will actually leave some variables uninitialized, and as a result, will result in some corruption of some critical structures and result in code execution. So the one issue with this attack surface is that it actually requires an elevation of privilege on the guest operating system to reach, but in certain cases that is possible. Now, one area that a lot of people have looked at is virtual printing, and there's been several good white papers released on this topic, and in virtual machine, or at least in VMware, they're using some thin print technology from a third party to actually replicate the host printers, and it's actually enabled by default in VMware Fusion and disabled by default in VMware Workstation. Actually, to enable it in Workstation, you have to use an administrative action to do that. But once it's enabled, the serial port is configured, and you can actually communicate with the host printers that way, allowing you to possibly trigger some memory corruption vulnerabilities in this third-party code. Here's the screens of what it would look like if you want to enable those so you can actually start doing work. There are people who do print from their virtual machines, so it may be enabled depending on what you're doing. Again, the requests are sent from the guest to host over COM1, and this communicates with vprint proxy over some named pipes, and this is running at medium integrity. And the important thing is a lot of the parsing of the imagery and stuff like that is done inside of tpview.dll, and so that's where you're going to want to start auditing. It does support parsing of various file formats, including JPEG 2000 and TrueType font, and there has been a lot of bugs discovered in this attack surface. We have purchased a lot of them and disclosed them. So some of them are dying, but there are probably more in there for you to look at. Now, we're at OffensiveCon, so let's actually start talking about a little bit of exploitation. And what you're going to see over the next 3 exploits that we're going to kind of deep dive is that it goes from kind of easier to really complicated. And we'll show you some techniques that are available for you to do heat massaging and doing where to put your ROP payloads and et cetera to help you gain code execution on VMware. So I'll pass it over to Abdul, where he'll go over this drag and drop use after free vulnerability.
Okay, so this is the first bug that I'm going to be talking about. We basically received this bug back in March last year, exactly 1 week before Pwn2Own, and we believe that it was a defensive submissions of some sort. And by defensive, I mean some of the Pwn2Own contestants would start trying to burn as much bugs as they can before the actual contest, just to increase the odds of them winning against other teams. So that's what we call defensive submission. It's kind of slick. So yeah. Anyways, so when we received this bug, we basically received this POC, exactly this POC. And it was a Python script that basically called RPC tool with these exact RPC functions. So what it actually does, it sets the version, the DND version to 2, then retrieves it, sets it to 3, retrieves it, and then it calls the DND function. So what happens here is that when you change between versions, then it's going to cause a free to be done. Then eventually, when you call any DND function, it doesn't have to be that DND function, then you're going to trigger a reuse. So personally, I was kind of surprised because I've never seen something like that before, specifically in VMware. Like, I come from a browser exploitation background, so this was kind of challenging. So when I ran the POC, it basically looked like the following, exactly the same as we would see in a typical use after free in a browser, basically dereferencing some address. So the first thing that I did is basically run bang heap -p-a on it, and then I got this nice call stack of the free, and then I totally understood that it's a use after free at this moment. The next thing was to find out exactly where it has been allocated and the size of it. So again, because I come from a browser exploitation background, what I did is I set a breakpoint before the free happens, and then ran bang heap -p-a on the address. Then I got exactly what has been allocated with the size of it. So it's basically pretty cool until now. Okay, so going back to IDA, so why did this exactly happen? So after the allocation, it calls a function that does a bunch of initialization on the object and then leaves a reference in another object, which is of size 30. When the free happens, it basically doesn't keep track of this reference and then just forgets that it has a reference somewhere. Later, when you reuse or when you call the ND function, then it's going to reuse that exact reference, and that's where the problem happens. So exploitation. In any use after free scenario, you have to ask yourself the following questions. What's the size of the object? How can I actually reclaim that free object? Can I leak memory? Can I get code execution out of it? Can I do both? So in this specific bug, we cannot actually leak memory because it's a straight RCE. So we're going to assume that we have a leak somehow. Personally, I used the memory leak from Tencent back in Pwn2Own to exploit this bug, well, to chain 2 bugs together, right? And the memory leak that I used was a simple call, a simple backdoor call through the high band mode, and basically it just dumps a bunch of memory to you. It's an initialized memory issue. So how can we reclaim memory? So I started sending actually random RPC packets, and I found out that you can definitely reclaim the freed memory through RPC methods. So we don't really have the luxury of JavaScript here, like browsers and stuff like that. So we have to play by the rules. And by the rules, it means you only have to do it through RPC functions. You might be able to do it through other means, but RPC is the easiest. I found out that there's a method that takes a string and basically sets whatever you give the string as a temporary folder for the guest OS, for the VM tools guest OS. I tried that, and I was able to override the freed memory. But later I found out that I don't even need to call a valid RPC function. You just send a bunch of A's as an RPC request with exactly the same size, and you would actually override that freed memory. And it was pretty simple. So once we have that, the next thing we should worry about is basically what should we do next? Where should we place our payload? How can we place our payload and all that kind of stuff? So I started reversing a little bit, and I stumbled across this function, Unity window content start. And basically it sets some parameters of the packet that you send, the Unity packet. It sets them in global variables. And basically it sets 2 D words in 2 global variables. So eventually you can set a 64-bit. Combined together, they can be a 64-bit address. So what I did is basically I found a simple wrap chain that basically exchanges RSP with RDI and just set it to that. Specifically, I did that because RDI at crash time points to my packet. So in a nutshell, the way it works, first you have to send the Unity packet. So it stores the single wrap chain address in a deterministic place. And then trigger the free, overwrite it, and then trigger the bug. So basically, visually, it looks like the following, which is you have the global variable pointing to the wrap chain, and at code execution, you're going to have it switch, and then just have the rest of your wrap executed. As for the wrap specifically, in version 12, there's an RWX region in VMware. So all you have to do is just copy your shellcode, place it there, and jump to it. Simple as that. And you can actually use this. You can generate some kind of universal wrap chain for that and use it for all RPC exploits. So this is how it looks like in action. So we actually wrote this exploit in Python using our RPC send module. My module, not Jasiel's. And it's pretty quick. All right, so the next one I'm going to be discussing is a heap-based buffer overflow, which we actually got as well the week before Ponto, and it was patched that week as well. And we believe it was a defensive submission as well. This is a little bit more complicated to exploit because it's a heap overflow. All right, so basically when you're drag and dropping a file that exceeds the actual packet size, then it has to be fragmented. And the issue happens when you're trying to reassemble these fragmented packets. So basically, the core issue lies in the function called transport buff append packet. So what happens is it gets the first packet, it does a bunch of checks to it, and then it gets executed again, parses the second packet, and basically it doesn't do a bunch of checks to it. So it just copies the data of the second packet, and you would be able to overflow a bunch of overflow a buffer. Specifically, when it starts parsing the first packet, it allocates an object of size A8, right? And then it copies the data of the first packet to that specific object. The second packet just grabs, since we actually control, in this case, the offset and the size, so we can grab the data of that packet and copy it, and that's where the overflow actually happens. So visually, in a normal operation. So you have the first packet. So first of all, the 2 packets have to have the same sequence number, or else it's not going to parse the second packet. So this is the first packet. When it gets parsed, you have a buffer or an object of size A8, and then it copies it. Next, you have the second packet with the same sequence number. It copies it. So this is legit. Everything's fine. Normal operation. So when we're trying to trigger the crash, first packet allocates, copies the data. Second packet, because we control how much we want to write, and then we're just going to overflow it. So the nice thing about this bug is that if we were able to trigger it reliably without actually causing a lot of mess, since it's a heap issue, then we can trigger that multiple times. And since we can trigger that multiple times, then we can leak memory first, and then we can get code execution out of it. So theoretically, how do we exploit heap overflows? Theoretically, you have your target object, and you have a bunch of allocations there. You overflow, and then you kind of overwrite something, right? If in the browser world, typically we overwrite a size, the length of a certain object, and then achieve arbitrary read and write. Or you can overwrite a vtable and just get RC out of it. Depends on the scenario that you want to follow. But again, if you want to do this in VMware, we need a way to massage the heap, and we need a way to create these allocations and deallocations, which is not as easy as we can do it in the browser world. So there are two functions that would help us do this. It's infoset and infoget. Basically, infoset allows us to create variables, the guest info variables, and you can give it the string, a string as an argument. It's a controlled string, so basically we can allocate whatever we want, whatever size. And then we can retrieve whatever is inside that variable through infoget. So this is ideal for us if we want to create a bunch of allocations of the same size. So it basically solves our problem, well, part of our problem. So here's the action plan. Let's allocate a bunch of objects of size A8, right, using infoset. And then let's free a bunch of, let's poke holes, free a bunch of objects. Let's throw the target object there, allocate the target object, the one that we're going to overflow. Let's close all the holes, and let's trigger the overflow, right? So that's typically how we can do it. So this is pretty nice. It looks legit, but the problem is that these objects, these string objects that we're creating are useless. Basically, they only have a heap address followed by a string, so that doesn't really allow us to leak a bunch of stuff. So how can we actually do it? We probably have to put some kind of C++ object, some kind of drag and drop object that contains some kind of interesting pointer that we can get VMware VMX base address out of. So here's what we can actually do. We can achieve that by setting the drag and drop version to 3 and then retrieving it, setting the copy paste version to 3 and retrieving it, and it's basically going to create a drag and drop or copy paste address object of the same size. So first, let's go back again, allocate a bunch of objects, free, and then try to throw that DND or CP object there. That's the one that I actually want to leak the address out of. Then throw our target object before that, fill the holes, and trigger the overflow, and basically try to leak something out of that object. So the only caveat here is that we need to make sure that these objects are created before each other. So the one that we have to leak should be created after the target one, and that's going to be a little bit problematic. I was able to actually do it by massaging the heap, so I was able to get between 70 and 80% success rate. But if you want to do it, if you want to keep testing the same VM more than 20 times, then at one point it just stopped allocating these objects the way I want. So if you want to test this, you have to always start from a clean state at least. And eventually you're going to end up with something like this, and we're going to end up leaking the address there. So this is basically how it looks like. So it's going to follow. This is the exploit that I wrote for leaking. Basically, it's going to follow exactly the same thing. Allocate a bunch of objects, trigger some holes, throw the C++ object there, and then trigger the overflow. So in this case, because we don't really know where the target object is, so we might have to keep overflowing and reading back, keep overflowing, reading back until we read something meaningful to us. So basically, this shows the address. So as for RCE, since we were able to basically get or leak information out of that object, then we only have to overflow one more time, right? Override that object, and then trigger a DND function or a CP function. It depends on what gets allocated there. It can be a DND or a CP. And once we do that, we can use the same exact trick that we use in the use after free to get the ROP chain executed and stuff like that. It's the same thing. So putting it all together, basically, it's going to trigger the bug multiple times, first to leak and then to get the RC. Okay. So the last bug there, it's your research section, but I was going to introduce you for them. Go ahead.
So the last bug we're going to go over is an uninitialized variable on the stack in VMware. And this one was given to us by 360 Chihu. This is also the most ridiculous exploit chain of, I think, all of March, or last year's Pwn to Own. We've been showing like graphics to try and help explain all the bugs. I tried to do one for this and completely failed, and so I'm going to show some extremely basic code just so we understand the vuln before we get to the exploitation part. So here we have some pseudo C that I only realized the last try run is technically invalid. But we have a struct, and we have two member variables, A and B. They're both D words. Where we then have this function where we are defining a struct, and then we are initializing those. So by defining it, it's not going to be initialized to anything, and it's going to be whatever the contents of memory are at that point. Then we're assigning to them, so then there'll be 41, 41, 41, and 42, 42, 42. Then we call this doStuff function, which it's going to get a pointer, and when it goes to act and use the A and B member variables, they're going to be the values that we specified. So the vulnerable condition, the bad condition, is where we have this example struct, exact same thing, but we're not initializing. So when doStuff goes to use A and B, it's going to be whatever's in memory. And as a result, you could have indexes that are completely invalid or pointers that are unsafe to dereference, all sorts of things. Now, the bug itself was found by 360 by fuzzing. That's as much information as I have as to how they found it. My suspicion is that they were fuzzing using MetalKit or something, and then they got a crash and they started reversing out of that. This particular function is called by the SVGA 3D command readback O table handler, and the issue is in the last two function calls here. So we have this struct that's allocated on the stack, and v2, I should have typed it better, but v2 is the beginning of that structure. And then we have these two functions that are being called with v2 or with a reference to v2 as an argument. And what's going on is that first function is responsible for initializing that structure, and then it returns either null or a pointer. And then the second one is responsible for cleaning it up. And there's no check on the return value from the first one to know whether or not it's safe to actually to call the second function. And so looking at those functions side by side, the one on the left is the one that initializes, the one on the right is the one that cleans things up. The main thing to keep in mind, because I realize it's probably small, is you have A4, the fourth argument, and that's the pointer to the structure, but there are ways of getting this function to early exit and return 0, where A4 is not going to be touched at all. So if it's not initialized by the caller, it's not going to be initialized by this function, and you'll have a structure that's completely invalid. The main thing to note about the cleanup function is you have some checking of flags based on that structure, but there's also a call to free by dereferencing pointers. So with this bug, we can dereference a value in memory or on the stack, but we don't necessarily know what it is. So the exploitation action plan is to try and make this useful. There are no functions, no SVGA 3D functions that will give us direct control, so we can't directly set any of those bytes that will be used to free. And I only showed one free, there's actually two, one at offset 16 and one at like 32 or something. What we can do is there's another SVGA command, SVGA 3D command set render target, and that'll put the pointer for a mob, a memory object, onto the stack right at that offset. And then there's another function, draw indexed, SVGA 3D command draw indexed, which will set the flags appropriately so that we can then call readback O table and trigger a use after free of a memory object. So the general idea is free a buffer, trigger use after free, and then use that to trigger type confusion. And that's what 360 did 4 times in a row to exploit this bug. So kind of looking at it all together, the attack timeline is set up a stack with a reference to an allocated object by using set render target, then call draw indexed, then call readback O table to take advantage of the vulnerable code path, and then reclaim the memory. The first time it does it, it's doing it so that you have a mob, a memory object that it can reference over and over again for the other 3 times. The second time is to force type confusion, and it uses type confusion to trigger an out-of-bounds read to leak a heap pointer. Once they leak the heap pointer, they trigger another type confusion bug so that they can leak a function pointer in VMware VMX. And once they have both of those, they force a free of that object and replace that with a custom object that has a pointer to a ret, and then it'll return back into their ROP chain. So trying to help visualize that, because that's ridiculous. So we've got mob 0 pointing to this blue block here. Gray blocks will mean free. So we start off by allocating mob 0, and then we immediately free it, and we now have an ID for this memory object that is not actually backed by a buffer. It's now backed by a freed buffer, but we can continue referencing it and we use it. And so every time I free any, or I say we're freeing any object, what's actually happening is we're going through the dance of calling set render target, followed by a call to draw indexed, followed by a call to read back O table to trigger the bug over again and free mob 0. So then we allocate struct 1 and then immediately free it. And so now we have mob 0 and struct 1 both pointing to the same address in memory. And we allocate, at this point we have type confusion and we can do all sorts of stuff, but we, in order to take advantage of it, allocate yet another mob, and this time modify the struct at offset hex 58, which happens to be the mob's size field. And we modify it from, I think, hex 60 to hex 1000, so that we can then read data back. Modified. And the way the read back happens is by copying data from the mob to the SVGA surface, and from the SVGA surface to GMR. GMR is guest memory region. Once that's been done, then we can do a read of the host's video RAM and read out the values. At that point, we have a leak of heap buffer, or of a heap pointer, and we know roughly where we are in memory. So now it's a matter of leaking out a function pointer. So free mob 1. Now allocate a different struct. This struct has a function pointer within it. Do the same surface copy dance so that we can leak out a pointer. So this time we're only leaking out 8 bytes because we know the exact offset of the function pointer within the struct. Now we have a heap pointer and a function pointer in VMware VMX, so free the struct one last time and then allocate one more allocate one more buffer on top of it, this time using set shader, so that we can fully control the entire buffer. And the function pointer will be to a function tail in VMware VMX that will trigger a return and return into the rest of the payload, which is the beginning part of the buffer. And I'm going to show a video of the exploit. So 360 did escape from VMware, but they actually started this off as a full remote chain from edge. The edge chain starts off with a out-of-bounds read, or out-of-bounds access in arrays in Chakra. I'm going to actually skip through a good chunk of it because the bug itself requires massive allocations of arrays to the point where it takes 1.5 minutes to exploit the user land portion.
So before you jump ahead there, just imagine what these guys are experiencing. I mean, now you know how complicated this one part of this exploit chain is. They're sitting there at Pwn Own with a bunch of cameras on them, people standing in the audience, $100,000 on the line, and this is what has to happen. It's absolutely ridiculous when you think about all the work that went into this exploit chain to actually go from edge all the way out of the virtual machine itself. And just what we described now is a very small portion of what actually was going on. So
could also see just how nervous they were, like after the user land portion finished, because that's where things get incredibly unstable. Because what happens is they have the user land exploit, and it's all JavaScript and HTML, and they use that to drop a DLL on disk, which they then call load library on. That triggers a kernel bug it's in window hooks in win32k.sys, and it's an untrusted pointer deref. Once they have code execution in ring 0, they use that they drop another file, this time a .sys, a driver, and they load that, kill any process that's gonna do anything graphical, because they can't have anything graphical happen, and then they wait 25 seconds just to make sure nothing wonky is going to happen, and then they let their exploit go. And it works. It's amazing because it is very much a one-shot deal where anything can cause it to fail. So you can see it just resized and then boom, calc. During Pwn to Own, it actually worked. And then it's running as medium. During Pwn to Own, it actually ran and worked, I think, the first time,
it was
which
the first
is
time.
ridiculous. It's amazing how stable it is given the sheer amount of effort that they went through just to get it exploitable. We didn't talk about the patches for any of the other bugs, but I like this one just because it's so incredibly simple. Previously, when we first looked at the bug, the last two functions being called were just being called in sequence, whereas here the first one is now in an if block. Stupid, simple fix, and it's just kind of funny that a bug that simple was still able to be used for VMware Escape. Before I turn it over to Brian for the conclusion, one thing that we always experience as part of Pwn to Own is the vendor disclosure. And as part of that, we do a vendor dupe check. We ask them if they have ever seen this vulnerability before. And you can tell a lot about a vendor based on how they respond. A lot of the vendors, they have bug trackers, and they will go check the bug trackers. Sometimes the people they have sent are so knowledgeable about the code base that they can say, actually, no, I know this is unique because I know every bug that we have open, and this is not like any of those, or this is a completely different attack surface. One vendor, one year, all they did was do a build against tip of tree, and it crashed, so they call that unknown to them. VMware, on the other hand, they did a patch right before Pwn to Own last year, and this chain, the SVGA chain, was the first bug we gave them. For the second one we gave them, I handed them the USB stick and said, hey, let me know if there are any dupes, or if this is a dupe or known to you. And while the USB key is still in his hand, he looks at me and says, oh yeah, this is unique. I'm just looking at him dumbfounded because I can see it in his hand, and I know he can't read a USB key from his hand. That's ridiculous. But he said that we patched every security bug that we know of last week, and you're telling me that this is different from the bug that you gave me earlier a couple hours ago, so this must be unique to me as well. And that is a terrifying notion for something that, like, this is a product that a lot of people use as a security boundary, and I think it's terrifying that that's their response, that they don't know any other security issues. Just kind of an interesting takeaway that I like telling that story. VMware probably doesn't, but yeah. Turn it over to Brian.
So yeah, I love that story because it kind of shows that there is a lot of open space here for people in this room to go do research and find vulnerabilities in this attack surface. I mean, most of us in this room probably use these products every single day, either for vulnerability research or for malware research or who write malware or whatever it is. It's important to understand that there is actually quite a bit of attack surface out there. There is previous research, and one of the things we like to do internally is publish as much research as we get through our program to kind of help people find bugs and learn about how to protect against those types of vulnerabilities. And so VMware does have a decent attack surface. We talked about 5 different areas at the beginning of the talk, and there's more out there that you can go after. It's very large, and they're always adding new things like XCHCI for where bugs can be discovered.
So one thing that they do that makes things a lot easier as far as reversing goes is for ESXi, Fusion, and Workstation on Linux, Windows as well. They have VMware VMX, but they also have VMware VMX-debug, which, as you imagine, is debug and has a lot more strings, but also function names. And some of the functions that they've hidden the names for in, say, Fusion, they have not in Workstation, or they haven't in ESXi. So if you have all 3 open at the same time, you can kind of compare and get a much larger picture, which makes it much easier when you're reversing. Just an aside.
Yep. And some of the hardest parts is actually just finding that initial vulnerability. I mean, if you can find a vulnerability in guest RPC, what we've shown you today, there are relatively easy ways to go about weaponizing that vulnerability and taking it to the next level. We do know that VMware is actively involved in kind of courting the research community. They did step up this year and sponsor the contest and trying to encourage people to do responsible disclosures through contests like Pwn to Own. But when you look at what's available, when you find a vulnerability, some of those some of those techniques that we showed you can actually help you get to that point of winning, $70,000 at contests and things like that. So the other thing to know is that the mitigation space kind of looks like the browser did 5 years ago. Back when Internet Explorer was basically a punching bag for everybody and their fuzzer, and use after frees were falling from the sky. The mitigations against those types of vulnerabilities just really didn't exist until recently with isolated heap and memory protection and some of the other things. VMware is not at that same place, right, when it comes to mitigation. So, they've got ASLR in depth, but once you get down to vulnerability-specific mitigations and things that could be done to harden very, unique vulnerabilities, it's just not there yet. So, and I think that will come with time as people do more research and disclose bugs and to the vendor, they'll actually get around to fixing some of those mitigation weaknesses that they have. And if you do find vulnerabilities, from this presentation, or you do use the exploit techniques, and you want to come out and disclose them to us, we do purchase them. We do run this major contest in March where we are giving away $70,000, and we'd love to give you $70,000 for research that you've done. So come on out and compromise some VMware targets for us. You got any questions?
Thank you.
All right, lots of effort. So 2 quick questions. You mentioned the VMWare debug versions. Is that publicly available, easy to get? Do you have to be on a
So
list?
it is available in VMware.
It's part of the installation. So on ESXi, if you do a PS and find where VMware VMX is, right in the same directory will be VMware VMX debug. Same for Workstation and Fusion.
Cool. And then are there any considerations with the things you've talked about that would apply to ESXi? Or is that just once you get into like a landing stage?
Some of the RPC stuff doesn't apply in ESXi. Rather, some of the code paths are there, but there are checks that will prevent it from running in ESXi. SVGA is present.
SVGA is present, so if you
Don't know
find
about USB.
USB, the bug that got patched is present as well.
Okay.
So for SVGA and XHCI, they are present. For RPC, they can be a little bit different. Some functionalities are not available in ESXi.
Drag and drop, for example,
Yeah.
not at all present in ESXi.
Yep.
Great, thanks.
Getting his exercise in.
Hello. Just one question. How many time do you spend to write the last exploit?
Last exploit.
Yes, the last one.
So the whole chain was 3.5 minutes, right?
Yeah.
Well, if you want to talk to the browser one
So
specifically.
fully exploited, I think 360 had multiple people, but they spent, I think, a month finding and exploiting that
Yeah.
bug.
Okay.
But they had a team of people working on it, so,
Okay.
yeah.
Thanks.
You can go.
Sorry?
If you have a question, continue.
Oh, no, it's fine. Thank you.
I was wondering about the heap allocator actually, because it looked really easy when you exploited it, like a low fragmentation heap on Windows 7 or something. So,
So this
what was that?
So this was exploited on Windows 10.
Yeah, I saw that.
So you definitely need to do some massaging and LFH stuff initially before you actually start massaging, because basically you're allocating A8, like object of of a certain size. So you need to make sure they actually land next to each other. So you should do a step before that, specifically with LFH, to have these allocations after that allocated next to each other.
Okay, so just an additional technique for Windows 10.
Just enabling, activating LFH for these type of allocations.
Okay.
Yeah.
I have a question, I'm sorry. Yeah. We know that the Chinese company, especially Qihu 360, they're known for disclosing bugs to you, right? And there is a language barrier when it comes from translating Chinese documentations to English. We know most of them most of the bugs, they don't get translated. Like we don't know up to what level of research they're already into, right? Do you have any plans of, I know that you're already acting as a bridge between the researchers in China, and right now what you're doing is traditionally, actually, you're being the bridge between their research team and us. Do you plan to continue to do so? And also, do you plan to continue to do, like, have their research papers translated maybe into English? We know that there's a gap, right? Do you do agree to that?
So I'll say a little bit. So basically, yes, there is a translation problem, especially with the white papers. So I remember at Pwn2Own, 360 had their paper written in Chinese, and one
For
of the
this
guys,
bug in particular.
yeah, and one of the guys was actually translating it. Their guys translating it in English and writing it in English. It's not the best. We actually have a guy on our team, Vincent Lee, who helps us with the translation. He's originally from Hong Kong, but definitely yes, there's a huge language barrier. Especially with the research, and it's not always well documented. So we have to dig a lot into code to understand what's going on, even with the translation or the white paper that they actually give to us. If that answers your question. So will we actually be the bridge? Hopefully we will. It depends on whether or not they're gonna keep sending us these bugs and participate at Pwn2Own.
So who does the bugs go to, 0DM or you?
You should always sell to us.
Yeah.
Any more questions? Thank you.
Thank
Thank you
you
very much.